Hello everyone. Let us start the lecture today. So first we will see what are the things that we already have covered previously. So we have seen what is sensors and transducers. I have discussed that in the previous lecture as well. We have seen the types of measurements. What are the different types of measurements for different sensors, which is again very important. We have seen different terminologies associated with sensors. This is something that we should discuss elaborately so that we get to know what are the terminologies and how we should tune those terminologies for a certain application. We also have checked materials and multidisciplinary aspects associated with sensors. So today let us start with different terminologies that we have listed in one of the lectures previously. So in that lectures we have seen that there are almost I think 20 different terminologies that we need to check when we design a particular sensor for certain application. Although I would say that there are many other terminologies which I did not list in that lecture, but while we are discussing, probably we will again bring in those aspects as well. So today we will start with our first terminology associated with sensor, which is known as accuracy. Now from the term itself, it is very clear that this particular terminology determines or gives you an indication how accurate your sensor is. So accuracy literally means the correctness of any system, that is how accurate or correct is the measurement. So again I will take an example of temperature sensor. I mean, if we take that example, then if you have a sensor that can measure temperature, then accuracy will give you that how correctly it is measuring temperature of certain object or an environment. Okay, so let us understand this in more details. So here let us consider this is the sensor. Okay, we have an input which is usually stimulus, and then we have an output which is, in this case if it is an electronic sensor, then we can consider it as voltage or current, whatever it is, based on the nature of the sensor. So the input, if we consider say temperature, then it's a temperature sensor, right? We usually get a relation between the input and output. For example, say the input and output is related linearly. So what is a linear function? Say y equal to mx plus c, right? So this y is your output and this x is your input, and here we have shown you the curve that defines if your input is say in here, then what should be the output. So this actual curve is also known as calibration curve, and we will discuss that calibration curve in the coming lectures. But for the time being, let us consider that this is the nature that the sensor follows as far as the input and output is concerned. Now let us consider for certain measurement A1. In this case you can take that measurement as 50 degrees centigrade. Say for certain measurement, because we have taken an example of temperature sensor, that's why your input is temperature. So let us, for 50 degrees centigrade, you have received an output which is here, this red dot. However, as per the actual curve, your output should be somewhere here, but instead you received the output somewhere here. So if we consider this output, then this output actually corresponds to the input that falls in the actual curve somewhere here, and the corresponding input value is A2. Say this is 55 degree. I repeat, you have a sensor, temperature sensor. You put this temperature sensor inside a chamber. Okay, say this is the chamber under consideration, and the temperature inside the chamber you kept as 50 degrees centigrade, and the output you received from this sensor somewhere here, say you are using a multimeter to get the output. So that output that you can see in this multimeter, that shows a value which is this one. However, as for the actual curve, if you extend this value is intersecting the actual curve in here, which corresponds to 55 degrees centigrade. Is that clear? You are measuring 50 degrees centigrade, but the output you received, that indicates 55 degrees centigrade as per the actual curve. So there is an inaccuracy of 5 degrees centigrade. So this inaccuracy is something that we need to measure. So accuracy basically is a measurement of inaccuracy. So we first determine what is the inaccuracy associated with a system, and then we define the accuracy. So this accuracy of a sensor should be very high. Usually we want 100% accurate sensor, so that there is no error associated with the sensor measurement. But in practice, you will find achieving 100% accuracy is something very difficult. Why? Because if you have a temperature sensor, it will also get influenced with other parameters where it is placed, other parameters of the environment where it is placed. So other parameters meaning, for example, say humidity or say some other disturbance which actually influence the temperature sensor response. So in many cases you will find that the sensor is not 100% accurate, but it should be very highly accurate, say 99%, 98%, depending on the application. If the application, for example, is robotic surgery, then very high accuracy is required, because the application is of that sort. So sometimes we can compromise the accuracy to some extent based on the application. For example, if you are designing a temperature sensor to measure the temperature inside a refrigerator, even if there is 2-3 degrees centigrade inaccuracy associated with it, if it's an household refrigerator, one may say okay, it's fine. But again, it depends. We usually try to use a sensor which is highly accurate, but even if it is not that high, for certain application it's to some extent fine, but for certain application which is of higher significance, we need as accurate as possible, ideally 100% accurate. So accuracy is something that we should definitely check in a sensor. Then there is another term which is known as precision. I told previously also, accuracy and precision are often used interchangeably. They are often used interchangeably, but as far as the sensor technologies are concerned, they are very different. Now we will take the example of the accuracy again, and we'll try to see what is precision. So as I have said, that if this is your actual curve for say A1 value, which is 50 degrees centigrade, your output should come here, right? But you have received the output here, right? So for 50 degrees centigrade, for example, your output should be here in the actual curve. It should fall on the actual curve, but you are getting an output somewhere here, and this value corresponds to input A2. right? And that is why you have seen an inaccuracy in the entire system. However, let us say you have placed the sensor again inside that furnace or say oven, and you are doing an experiment where, say, this is where your sensor is placed. You are taking the output from certain device outside, say it's the measuring device where you are getting the output, and you are doing an experiment that you are putting the sensor inside that chamber, measuring the output for 50 degrees centigrade, and then taking that sensor out of the chamber. When this sensor is in the normal temperature, again you put this thing inside the chamber. So the experiment is, you have the sensor, you put this in the oven, measure the output value of the sensor for 50 degrees centigrade, you take the sensor out, and when the sensor again comes back to the normal temperature, again you put it inside the oven to measure the output again. So if you do this particular experiment 100 times, so you are taking 100 different values for 50 degrees centigrade only with the same sensor, and what you have seen is, every time you measure the output for 50 degrees centigrade, you are getting a value exactly in this point. I repeat, every time you measure the output of the temperature sensor for 50 degrees centigrade, you are getting a value which is this one only. Then we will say that this sensor is very much precise, in fact 100% precise. The second case is, you may find that every time you measure the value, output value of the sensor for 50 degrees centigrade, the output that you get is very close to the one that you have received previously, right? Very close. Then we can say that the precision is very high. There can be another situation that every time you measure the output value of the sensor for 50 degrees centigrade only, you are getting values that are scattered, very much scattered. Then the precision of the sensor is very low, or we can say that it's less precise. So precision is the probability distribution of outputs that you get. If your distribution of output is very sharp, then you can say that the precision is very high. Ideally, for a 100% precise sensor, you should get the value exactly at the same point every time you measure for a certain input. But in practice, you will find that there is certain deviation. For example, if for 50 degrees centigrade this sensor is giving an output, say 25 millivolt for the first experiment, maybe for the next experiment it can give 25.5 millivolt, and then if you do the experiment again, it may give 24.3 millivolt. Okay, but it's all the time very close to 25 millivolt. Then you can say that the distribution is very narrow. The distribution is very much narrow. Then we can consider that the sensor is very precise. However, the actual value should be somewhere else. So the difference between where I am getting the value and where the actual value should be is the accuracy. In fact, this is inaccuracy. We can call it inaccuracy, which is again in other words can be converted to accuracy. If the inaccuracy is 2%, that means it's 98% accurate, something like that, right? So accuracy cannot guarantee precision, and similarly precision also cannot guarantee accuracy. So they are very different as far as the sensor technologies are concerned, Okay. So precision is again a very important term. So a sensor can be very highly accurate but less precise. A sensor can be less accurate and less precise. A sensor can be highly accurate and highly precise. That is what we usually try to achieve. So a sensor should be highly accurate as well as highly precise. So that is our target when we develop a sensor. Again, based on the application that you have, there can be a small deviation, or you can compromise to some extent based on the application, right? But ideally your sensor should be highly accurate and highly precise. Then we have the one of the most important parameter, which is known as calibration. So calibration is the actual curve that you have shown, that we have seen maybe in the previous lectures. That is actually the calibration curve. So calibration curve is nothing but the relation between input and output. If your input is defined with small s, then the relation between the input and output will be your calibration. So we usually define it with an mathematical equation. If your capital S is, for example, say if your capital S is output and small s is input, then this function is your calibration function, and based on that function, whatever plot or curve you get, that is known as calibration curve. So each sensor follows a input output pattern, and the pattern might be different for different sensors of same batch also, if the fabrication process is not uniform. What I mean by that is, if your fabrication process is not very uniform, or if you do not define your fabrication process, then you will find that calibration curve or relation between input and output will vary for different batch of your sensors. So usually we first have to decide what should be our fabrication process, okay, if we want the sensor to work properly. So we try to achieve a linear characteristics between input and output. As I've said, we try to achieve this relation y equal to mx plus c, which is a equation of a straight line. So we try to achieve a linear relation, because if you get linear relation between input and output, it becomes very much easier for us to connect the sensor with a system. Then the system will be less complicated. Okay, system is the circuit that actually drives the sensor. Okay, so but in practice you will find that input output relation may not be linear. It may be very different. Okay, it may be something like this, it can be something like this, or it can be even very different and can be an higher order polynomial. However, when you develop a sensor, the first thing that you should do is the calibration. So how do you figure out the calibration? So the process to figure out the calibration curve of a sensor is to use some known input value and check what is the output that you are receiving. What I mean by that is, let us take an example of temperature sensor again. So say you have prepared a temperature sensor, and this sensor gives different output value for different temperature. So what you will do is, you will first put this sensor into different temperature conditions, and then you will start measuring the output from this sensor using, say, any measurement like multimeter or source meter, whatever it is, based on the output that you are receiving. If it's a voltage output, you can measure it with multimeter. If it's a current output, then also you can measure it with multimeter. If it's an impedance output, say change in capacitance, then you need to use an LCR meter. So whatever is the output, or based on the sensor that you have fabricated, you have to decide the instrument which can measure the output of the sensor. If it is an FET based sensor, then you may need to check the output characteristics of this FET with different temperature. So once you decide the instrument that can measure the output of this sensor, in this case, if we consider the output is voltage, then we can use a multimeter. So you connect the entire sensor with a multimeter, both the terminals. If it is a 2-terminal device, both the terminal you can connect with a multimeter, and you can put the sensor in different temperature conditions, say on top of an hot plate, and then you are increasing the temperature from room temperature to certain values, say till 80 degrees centigrade, and then you start making a chart for each input value, what is the output that you are receiving. So say if the input is 25 degree, say room temperature, in this case we can consider 20 degrees centigrade. Okay, so if your input is 25 degree, you may get an output, say 5 millivolt. Okay, because you have considered the output to be voltage, right? Then you measure for 30 degrees centigrade, then 35 degrees centigrade, you change 5 degrees centigrade and start measuring the output. And then once you have enough data, say 10 different values, 15 different values, you start plotting the results into a graph. So x-axis should be temperature, output axis should be voltage. So input axis is temperature, output axis is voltage. Then for say 25 degrees centigrade, you have one value 30 degrees centigrade, you put another value 35 degrees centigrade, you have another value 40 degrees centigrade, you have another value, likewise you will find different other, and then you can join these to check how your input output characteristics look like. If they are falling into a fairly straight line, you can consider the input output characteristics of this particular sensor is linear. This input output characteristics you also have studied for different electronic devices. For example, for MOSFET, FET, the output characteristics of any electronic devices is basically the relation between input and output, right? If it is a MOSFET, you take the input and measure the output, whatever is the carb, you call it output characteristics of MOSFET, right? For FET also this is same. So this particular relation is the calibration curve for a particular sensor. So this is how you measure a calibration curve. Now based on that calibration curve only, you can decide what should be the system. So a system can only be designed, or a circuit can only be designed for a particular sensor once you know the input and output. This is true for other electronic devices as well. In analog circuits, probably you have studied that we consider each device as a black box, and what a circuit engineer mostly need is the relation between input and output. Once you know the input and output relation is something like this, then you can use this information to design a circuit, be it a switch, be it a amplifier, whatever it is. So circuit engineers or system engineers usually do not need the physics associated with a device. Once they know input and output relation, they can design a circuit for you. But as far as the sensor engineers are concerned, because input output relation is not something which is defined, so you may need to know the physics associated with it sometimes to figure out whether you can get a desired calibration curve or not. Okay, what I mean by that is, For example, if the calibration input output characteristics is something very random, then definitely that particular sensor is not suitable for certain application, right? Then in that case you have to change the sensor geometry or the sensor fabrication process so that you can get a certain sort of relation. However, I mean, I would say that even if it is very random, at times you can figure out some technique so that at least it can be used for a certain range or something of that sort, or at least for semi-qualitative, sometimes qualitative sensing. But again, it's a system level modifications that we may see in the future lectures. But in generally speaking, if it is very random, then you are not able to use that particular sensor for certain application. In that case, you have to go back to the device physics, you have to go back to the device geometry, and you have to make some modifications so that you can make it useful. Okay. The next very important parameter is sensitivity. So the sensitivity of a sensor is the change in the output that you can see for unit change in the input. What I mean by that is, again, if I take the example of say temperature sensor, say this is voltage, then you'll find that for each 1 degree change in the temperature, you are getting a certain amount of voltage, which is say 0.0035 millivolt. Okay. Then the sensitivity of that sensor will be 0.0035 millivolt per degree centigrade. Okay. So what I mean by that is, the sensitivity will give you the information about the incremental change in the output for unit change in the input, but that doesn't ensure that your sensor can measure each degree change of input, because to measure each degree change of input, you need an instrument or a system that can detect 0.0035 millivolt. So it is system dependent to some extent. This is the maximum possible resolution. I mean, I won't say resolution is something that we will discuss later as well. This is the maximum possible kind of performance you will get for per degree change as far as the temperature sensor is concerned. But this parameter is very important because this will give you an indication that what your sensor is capable of. So how do you measure it? From the definition itself, what I have said, it is very clear, it's nothing but the slope of that particular curve. So if you have a linear calibration curve, then if you figure out the slope of this curve, this actually shows for unit change in the input, what is the change in the output. So what you do in that case, you take a particular section, you measure what is the input change here, which is delta S, and you measure what is the output change here, which is delta Fs. So what is your sensitivity? For delta S, the output change is delta Fs. For one or unit change, the output should be delta Fs by delta S, which is nothing but your slope. So this is something which defines the sensitivity of your system. But if your calibration curve is not linear, if it is non-linear, say like this, then in that case you have multiple sensitivities at different ranges. For example, in this range the sensitivity is, the slope is this one, so you can consider the sensitivity is this one for say this range. For this range it's like this one, for this range it is this one, something like that. Then you have to divide your entire calibration into 2-3 different parts, and you have to figure out what is the approximate slope in that range. For a curve like this, ideally in each point you have different sensitivity because the slope is changing continuously. But to make the life easier, what you can do is you can take a subsection of this calibration curve and you can fit that section with a linear function, and then the slope of that linear function can be the sensitivity in that range. So if it is not linear, the calibration curve is not linear, then you have multiple sensitivities, and then you may calculate the average sensitivity, or you can report the average sensitivity. However, average sensitivity is not something which probably will give you the entire information about the sensor. You need to check what is the sensitivity at different ranges. That probably will be much useful as far as the system design and circuit design is concerned. So sensitivity is the measure of the output, incremental output, you can say change in output for unit change in input. So the sensitivity of a sensor is the output to the unit change of input. Okay, or here you may write sensitivity of a sensor is the change in output. You may also make it incremental change in output to the unit change of input, right? It's just the slope if you see. So let us see what are the take home messages from whatever we have discussed so far. The first one is accuracy and precision are two different very different parameters in sensor technologies. We have seen that a sensor can be highly accurate but less precise. A sensor can be highly accurate and highly precise, and so on and so forth. So these both terms are very different as far as the sensor technologies are concerned. Then we have seen that calibration curve is the relation between the stimulus, that is input, and the sensor output. So it's nothing but the output characteristics of a device. If you think from the device perspective, for example, if you think about MOSFET, the MOSFET output characteristics is nothing but the relation between the input to that MOSFET to the output. So in sensor also it is same. Calibration curve is the relation between input and the output of the sensor. Sensitivity does not always ensure the unit value of input detection. I also said that during the sensitivity discussion, that sensitivity does not ensure that you can detect unit change in the input. This is just a parameter and will give you certain indication how capable your sensor is. So to make it more clear, what I have said is, for example, for each degree change, if it is a temperature sensor, for each degree change, if your sensor output changes by say 20 microvolt and the sensor is connected with a system which can measure minimum of say 2 millivolt change in voltage, then definitely the system will not be, or the entire sensor system will not be able to measure 1 degree change in output, because for 1 degree change in output it only gives 20 microvolt. So there must be a system that can also detect this 20 microvolt change. So sensitivity does not always ensure that your sensor or sensor system is capable of detecting unit change in the input, right? So there is a question, can a sensor with high sensitivity be less accurate? A sensor with high accuracy can be less precise, or a sensor with high precision can be less accurate. But the question is, can a sensor with high sensitivity be less accurate? That is, the sensor has very high sensitivity. What do I mean by very high sensitivity? If the curve is steeper, say if I take the characteristics to be linear and one calibration curve is this and another calibration curve is this one, then definitely the second curve has a higher slope. That means the second curve has higher sensitivity. So the question is, if a sensor has very high sensitivity, can it be less accurate? Let's think. You can think it and figure out whether it is possible or not. In the upcoming lectures, we will see other sensor terminologies. Till then, thank you.